What do you ask?
It's bad.
Do I have to do it for this class?
No, it's a
I just relying on my quick.
Okay, good morning everyone. Good morning. Alright, so we're going to solve another problem before we move on to better things in thermal heat transfer due to conduction. Okay. The problem statement has been posted on your Carmen page, so if you want you can refer to that. I'm going to write down the details as well myself. Before I do that, a couple of clarifications because I've been getting these questions quite often with regards to your homework. Okay. First things first, so far, until today's lecture, and things will start changing today, until today's lecture we have not included the effects of energy generation. Okay? So which tells us that if I am looking at steady state heat transfer, then I am talking about steady state heat transfer in the absence of energy generation. Okay? So there are two different things. So steady state implies the following. It implies that the rate of change of the stored mechanical and the thermal energy is zero. Stored mechanical and the internal thermal energy is zero, or we typically write this as E dot stored is zero. This is all steady state states. What we have been doing is we don't have any heat generation whatsoever, so we have also been tacking on that additional term where we say there is no heat generation. So in steady state heat transfer, I can either have heat generation or no heat generation. Okay, so this does not imply E dot G need not be zero, okay, in this particular situation. So if we say steady state with no energy generation, then in such a situation you can say that E dot stored is zero, E dot generated is zero, and as a consequence the rate of change of the total energy within the control volume is zero. This is the situation that we have been looking at so far. And for such a situation, if we perform the conductive heat transfer that we had looked at a couple of lectures ago, you will end up with the following formula. For steady state with no energy generation, Q double prime conduction will end up giving you a linear temperature profile. So this is going to be K delta L T high T low. Only under this situation, when both E dot stored is zero and E dot G is zero, can you use this formula. And the obvious question is, okay, what if I have steady state conditions, but there is energy generated within the controlled volume? What happens to Q conduction? The expression is going to change. We're going to see that today, hopefully, or maybe on Monday. Okay. So in this situation, if I have steady state, but there is a certain amount of energy generated, positive or negative, depending on the process involved, what is the conductive heat flux? I have to use Fourier as well. So the main thing is Q double prime conduction in such a situation is not equal to that expression that we have just written. We have to come up with a different way of categorizing this kind of an energy transfer. Any questions before we proceed further? I want to make this very, very clear, very, very obvious. So far, we have seen only this particular situation where there is energy stored, rate of stored energy is 0, the energy generated. There are no sources of generation for us. We are soon going to change that. And when I do that, I can no longer take refuge in this particular equation. We have to derive something else. Okay? Alright, with that said, let's get to our problem. And I think a lot of questions that you may have on your homework will also be answered when we solve this particular problem. It's very similar in many ways to what you have in your homework. So problem. We have a thick slab made of a certain material. Okay. Let's say that K is the thermal conductivity. We don't know what it is. We are not given any information on that. You are told the following: the bottom and the sides of the slab are insulated. If you see hatched lines, it means it's an insulated surface. Okay? And we'll see the meaning of that very soon. So these are insulated. Bottom subscript B, top subscript capital T, this is insulated. Subscript is T. The temperature of the top surface is not known to us. You are told that there is some ambient air in bulk motion close to the surface, and the temperature is T infinity. The convection heat transfer coefficient between the ambient air and the top surface, let's say H suffix T, is given to us in the problem. I'm going to list all these variables. Then you are further told that this slab is sitting and surrounded by a very large room or a very large surrounding. Okay, so I'm just going to draw the surrounding here. Okay, so this is the surrounding whose temperature is T surround. And on top of that, you're also told, okay, the sun is shining and there is some radiant flux incident on the surface from the sun. Okay, so here is the sun. The following information is given to us. So T infinity is 20 degrees Celsius. We are told in this particular problem that T surrounding is T infinity. In general, as you will see from the second problem of your homework, the surrounding temperature, or the first problem, I don't know whichever one of that is, the surrounding temperature need not be the temperature of the fluid close to the surface. Okay, so this is something to keep in mind. So this is not in general true. In situations where you have a surrounding temperature and you're not told any information about it, then you can assume that, okay, unless I'm asked to find out what it is from the balance equations, I can assume that to be the same as the temperature of the ambient fluid, only in such situation. Okay? So it is very important that you list out all your assumptions carefully, go over your assumptions, see if there are any inconsistencies which will get caught when you solve the problem. You get some funky numbers, it's probably something wrong with the assumptions. Okay? Alright, then I'm given the heat transfer coefficient, convective heat transfer coefficient. This is 8 watts per meter square Kelvin. And furthermore, I'm told that the emissivity of the top surface, epsilon T, is given to me as some number, I think it's 0.25, if I recall, it's 0.25. Then I'm told that the reflectivity of the top surface to solar irradiation, which I'm going to write as rho sun, is 0.2. We'll talk about this in a bit. Then there's a certain amount of incident radiation from the sun. So this is G sun. We typically treat the radiation from the sun separate from the radiation from the surroundings. Okay, the reasons for this will become more obvious as we go into radiation heat transfer. For the time being, bear with me. If you have the sun, the radiant flux from the sun will be given as a separate number. Okay? You should not confuse that with the radiant flux from the surroundings. This is not G surrounding, and I'm going to say the surrounding as a subscript O so that I don't confuse SUR and SUN. So this is T naught. Okay? So this is G naught. G surrounding is G naught. G sun is different from G surrounding. And you are told that G sun is 600 watts per meter square. So this is a flux, which means that it has to have units of watts per meter square. And you are also told some additional information. Area of cross section that is available for heat transfer is going to be 1 meter square. So area A of the top, same as the bottom. This is 1 meter square. Typically when we talk about area, this is the area of the surface that is conversing with the ambient fluid and the surroundings. Okay, so for example, if I draw a 3D view of the slab, this is the view that you are seeing on the board there. This shaded piece is what you're seeing. The area that they are talking about, which is available for heat transfer on the top surface, is the area that is projected out of the page, okay, or whatever is here. So this is the area that is available for heat transfer. And you're told the thickness of the slab is 4 millimeters. So delta L, 4 millimeters, this is delta L. And the last piece of information given to us is that there is a certain amount of energy that is generated within the volume. This is a positive energy generation. It could be based on many things happening within the control volume, which we are not privy to. Could be an exothermic reaction, a nuclear reaction there. Could be energy supplied from an electrical device, which generates volumetric heat within the body, within the control volume. You are told this quantity is 100 watts per meter cube. Okay, so I'm going to write that here, Q dot, which is the energy generated per unit volume So this is in watts per meter cube, and this is given to us as 100 kilowatts per meter cube. I'm going to write that here. So Q dot is 100 kilowatts per meter cube. This is all information given to us. Things that you're asked to find, once again you'll see these details in the problem statement. I need to find the temperature of the top surface. The temperature of the top surface is what? And what is the conductive flux at the top surface? Okay, so I'm going to label a coordinate system now. Watch this. I'm going to say that the vertical direction is the x direction. I can say any direction to be the x direction. I just choose today the vertical to be called as x. So this is my x direction. The bottom of the plate is x is equal to 0. The top of the plate is x is equal to delta L. I am asked what is the conductive heat flux at x is equal to delta L. So Q double prime, conduction at x is equal to delta L is what? I'm going to slide both these panels up so that we can start drawing our control volumes and so on, and control surfaces. Alright, I hope the problem is clear to everybody. First things that we will do in any problem is we will list our assumptions. Okay? The assumptions. One-dimensional heat flow. We have not done anything besides one-dimensional flow so far. So 1D flow, and this is going to be in the vertical direction because the sides are insulated. People in the back, do you have a question? Okay, thank you. So we're going to assume that the direction of heat flow is vertical. I don't know if it is going to take place from the bottom to the top or the top to the bottom. We have to know what that is at some point. We're going to assume steady state, but with energy generation. Be careful. Which essentially implies that E dot stored is 0, but E dot G is not 0. Which can be given as the volume of the control volume equation.
So why are we assuming that energy is being generated in this problem?
Why are we assuming it? Because perhaps there is some chemical reaction taking place within the control volume. We don't know what the source of that generation is. All we are saying that, okay, hey, there is some process taking place inside, and this is the amount of generation per volume, per unit volume. Okay? So these are all external things that are happening. E dot G, we are going to write it as Q dot, little q dot, which is energy generated per unit volume multiplied by the volume. For this particular situation, the volume is fairly trivial. It is the surface area times the thickness delta L. So I'll write that out as well here for our situation. But we will soon start dealing with cylindrical surfaces and spherical control volumes and so on. So you've got to be careful. This is not true always. Okay, the volume is not necessarily just area times delta L. Alright, so this is not equal to 0. Which essentially says that I cannot use my nice conduction flux equation. Okay, so we cannot use couple more assumptions and then we are on our way. I'm going to assume that the surface, top surface is gray. And the surroundings are very large. Which tells me that the emissivity of the top surface is the same as its absorptivity to surrounding irradiation. Alpha naught, which I'm going to call as the absorptivity to the surrounding irradiation. And G naught, which I had written as G surrounding previously, just not to confuse with the sun, because I'm going to write G sun as well very soon. This is sigma T naught to the power 4. And we are also in turn assuming that T naught is the same as T infinity because we are not given any other information. If you are specifically given information on the surrounding temperature, please use that character. Okay? For us, °C, convert everything into Kelvin. So 20 plus 273, 293 Kelvin. All right. So these are reasonable assumptions, and you'll see very soon as we go into after we finish conduction and go into radiation that radiation is typically most of the times negligible unless the temperatures are fairly high. Usually, okay, usually. Not to say this is always the case. But for the time being, we'll include that as an effect in our problems. All right. My next step, I don't know what to do. So I start drawing the control surface, and I draw the control volume, and depending on how I draw the control surface, around the control volume or within the control volume, my energy balance will be subsequently different. Okay? So I draw the control volume as before. I draw a control surface around the control volume, so dotted lines. This is my control surface. And then I start looking at all the events that are taking place across the control surface. Energy transfer takes place across the control surfaces. There is energy generation within the control volume. So I'm going to have E dot G is not 0, E dot stored is 0 because I'm at steady state. Okay, so this is within the control volume. These are volumetric phenomena. Then we start listing one by one all of the fluxes that are occurring in the problem. Capital E is emissivity. Any surface at a temperature greater than 0 Kelvin is going to emit radiant energy. Okay? So I'm going to have capital E, which is E of the top surface. This is always going to be going out of the control surface from the top surface. Convection heat transfer. Do I know the direction? Do I know the temperature of the top surface? I don't. Do I know the temperature of the fluid? I do. But I have to assume something. So let me assume that the temperature of the top surface is greater than the temperature of the fluid outside. I don't know if this is true. I have an inkling that this might be true because I solved the problem before coming to class. But let's assume that this is the directionality. Okay? So this is Q double prime convection we don't know. Yes?
What would happen if we assumed it to be entering the surface? Like,
No difference.
okay.
Absolutely no difference. Because if it is entering the surface, then you just be flipping the directionality of this, and so this is, instead of being a term that comes in the E dot out, it will be a term in E dot in.
Okay.
That's all it does. So you're free to assume the direction of this guy. Completely fine. Okay? Then I have some radiant energy coming from the surroundings. I'm going to call that as alpha naught. G naught. This is the irradiation from the surrounding that is absorbed by the top surface. Okay? Then I'm going to have some irradiation from the sun. And there is only a portion of this that is going to be absorbed by the surface. A certain portion is going to be reflected. So I'm going to draw the absorbed portion here. This is alpha of the sun. Not alpha of the sun, alpha of the surface to the sun, I'm sorry. Absorptivity is a property of the surface. It's not a property of the sun. Emissivity is a property of the surface. It's not a property of the surrounding. The surrounding could have its own emissivity and absorptivity. If you have this special gray surface, then the following is true. Under what caveats is this true? We will see radiation heat transfer later. Alright. One thing I want to write down here. G in general, okay, is G absorbed, G reflected, G transmitted. We assume an opaque surface, so I got to write that out somewhere. So we assume an opaque surface. Which means that G transmitted is 0, so we get rid of this guy. G absorbed, I write it as alpha times G. So capital G is alpha G, which is the portion that is absorbed, a fraction of the irradiation absorbed, plus rho times G, where rho is the reflectivity. So this is reflectivity, this is absorptivity. So three things that happen for a surface, actually four. There is emissivity, which has nothing to do with irradiation. There is absorptivity, there is reflectivity, there is transmissivity. We don't have transmissivity, tau, because of the fact that we don't have any transmitted radiation, which is due to the fact that we have an opaque surface. But we do have the other two. It's common sense to see that I can cancel off this common term G so that I have the following equation. Alpha plus rho is equal to 1. This is true for any opaque surface. So that if I'm given 1, I can find the other. So alpha is 1 minus rho. This is for an opaque surface only. Or an opaque body, if you'd like to think of it. Okay. Are we done with this? Do you think? What about the bottom?
Insulated.
It's insulated, which means there is no energy transfer taking place across this control surface in the manner that I have drawn it. If I had drawn this within the control volume, things are different, and I'm going to do that next. Okay, so here, this is insulated, which means that there is no energy transfer across that control surface. In the manner that we have drawn. Okay, so this is going to be my figure number 1. This is perhaps sufficient to solve the problem, to find the temperature of the top surface, but before that, let me draw another control volume and draw the control surface within the control volume. Okay, so same slab. The bottom surface is insulated. My control volume is now, control surface is now drawn this way. Okay. I'm going to have a certain energy generation. So E dot G is not 0. This is figure 2. E dot G is not 0. E dot stored is 0. Steady state. What are the terms in terms of energy transfer? At the top control surface, I'm going to have a certain amount of, and I'm going to assume that the direction of conductive heat transfer is from the bottom to the top. Who knows? I don't know. But heat has to travel one way or the other. And if I'm assuming that the direction of convection is from the top surface to the fluid, then obviously if there is something going on here, the direction of conduction should be from the bottom to the top. Once again, I'm not sure. Just an assumption. We will see. Okay? So I'm going to say that there is a certain amount of energy transfer due to conduction entering the control surface. This is the conductive flux at the location x is equal to 0. Yes.
Is that arrow supposed to be going through the body, or is it
No,
supposed
I'm
to
just
stop?
drawing it out.
Okay.
It has to be within this one. I'm
Okay.
just running out of space.
Okay.
I should have drawn a bigger picture. Then I'm going to have something going out. Obviously, if heat comes in, it has to go out. So I'm just going to draw it this way. The significance of this is just energy transfer taking place across this control surface. It's not penetrating and going out through the body. Okay? It is taking place within the body, within the medium. There is no bulk motion within the medium, so the only form of energy transfer due to heat transfer is conduction, which is why we call it as conduction. This is Q conduction at x is equal to delta L. I don't know if this creature is the same as that creature. In the past, we have assumed them to be the same. And that was a consequence of saying that there was no energy generation. Now I cannot say that anymore. And you're going to see it in a minute. Okay? And of course, E dot G is not 0. E dot store is 0. So this is my second situation. So let's take a look at situation 1 and situation 2. Yes, coach.
Could you put those signs reversed or not? Does this still work kind of like the last situation?
It could. It could. But if I'm assuming that the direction of heat transfer from convection is from here to there, then it kind of implies that I'm saying the conduction is going to take place from the bottom to the top. Okay, if I reverse it, then things will be different. I'm completely free to assume what this direction is. The math will tell me whether I'm right or not. So one thing you want to remember, this is something I always tell people, don't trust your intuition, trust only the math. Alright, take one. It is just a Hail Mary, right? We are just drawing these things and hoping something sticks. So I'm taking one and I'm going to write the energy balance. Okay? So E dot N. What are the terms that are coming into the control surface? They're going to be alpha naught and then alpha of the sun. Alpha naught, G naught, alpha sun, G sun. Things that are going out. And just for fun, when I post my lecture notes, I'll take the direction of this to be opposite to what I was doing here. Okay? And you'll see we get the same answer. Yes?
Shouldn't you be multiplying those by
Areas, absolutely. Absolutely. The areas are the same for both, top and the bottom. And this has to deal with the top surface. So this is multiplied by 8. E dot out, the convective flux going out of the top surface multiplied by the area. Then I'm going to have E suffix T, which is the emitted flux multiplied by the area. Emission is completely different from the irradiation. Irradiation is a consequence of the surroundings. Emissivity is a consequence of the surface whose temperature you are trying to find out or whose temperature is known already. Okay, so they are mutually exclusive events. I can have one without the other. Most of the times, we will always have emission, because we are always looking at bodies greater than 0 Kelvin. Okay? E dot generated, Q times A times delta L, E dot stored is 0. write your energy balance equation. E dot in minus E dot out plus or minus E dot generated. In this situation, you are told in the problem that this is a positive heat generation taking place. So I'm going to pause positive sign there. This is equal to E dot stored, which is 0. E dot D is positive for us, so I'm just going to write down all these terms. So alpha naught G naught, which is sigma times T naught to the power 4, plus alpha of the sun, which is known to me as, because I'm given the reflectivity of the surface to the solar radiation, this is going to be 1 minus rho of the sun. Times G sun, which is a number that's given to me. It is not possible to use this very simple equation until we go through the math for radiative heat transfer. Okay? So at this point in time, if you have solar irradiation, it will be given to you. Multiplied by the area, all of this, minus convective heat flux, H top, is what I had assumed, I guess, times T top, T infinity, I'll multiply by the area eventually, and plus epsilon T sigma T to the power 4, multiplied by area, plus energy generation, because it's a positive quantity for us, plus Q dot A times delta L is 0. Cancel of the area, which is why I was kind of blasé about it at the beginning. All the terms here are known to us, information given to you, except for the temperature of the top surface. So this is unknown to me. And of course, this is unknown to me as well. This is going to be a fourth order polynomial in the unknown quantity. Solve for it. The details will be posted in my lecture notes. Will end up being approximately 376 Kelvin. Okay, approximately. Everything else is known to me. Alpha naught is given to me. And 1 minus rho sun. So alpha naught is the same as epsilon T, which is known. This is known. T naught is 20 plus 2, 73, 293 Kelvin. Rho of the sun is 0.25. This is known. G of the sun is 600 watts per meter square. HT is given to me as 8. This is 293 Kelvin. Q dot is 100 kilowatts, which is 100 times 10 to the power 3 watts per meter cube. Delta L was given to us as 4 millimeters. This is the answer we wanted. And this is happenstance. I did not know if this picture would help me solve the problem. I started off by drawing. Okay? Yes, sir.
What do you do when you have like multiple roots of the fourth order and then multiple of them are like actual numbers?
You will typically, in a problem, the numbers will be designed such that you will get only one positive root. Right. If you have two, then you have two choices. That's it. More fun. Okay. What about this guy? And I'm going to do one more thing. I need to do the following. I'm going to erase this panel here. And I'm going to draw two more control surfaces. you see the connection between this and mechanics, right? Because you keep drawing these control surfaces, and similar to how you draw free body diagrams. When you don't know what to do in a problem, you draw a free body diagram. We hope to have God that it helps you, if there is one. All right. Third and the fourth figures for me. Let's take a look at this bottom guy as the more interesting of the two. This is surface energy balance. Which means you are interested only in events taking place at that particular surface, which means that if you are doing surface energy balance, even if there is energy generation within the control volume, for your surface energy balance at that surface, E dot T is 0. I want to be very clear about this. For any surface energy balance, there is no volumetric phenomenon that will be taken into account. Okay? You will have only surface phenomena, things that are going out, coming in, and so on. Alright, now the bottom is insulated, so there is no energy transfer across the control surface here. But there is some energy transfer taking place through conduction at the control surface out there. So I'm going to draw it out as Q double prime, conduction at x is equal to 0. If I write energy balance, so this is scenario 3. If I write the energy balance, E dot in, E dot stored and all that is gone. E dot in is 0, E dot out is Q double prime, whatever. At x is equal to 0 is essentially going to be 0 because of the fact that there is nothing else going on. But let me not jump. I write the energy balance equation. All of these guys are history. I have only E dot out, which is minus Q double prime conduction multiplied by the area is equal to 0. This is where we bring in Fourier's law. If I just write it using Fourier's law, one-dimensional heat transfer, so this is minus k dt by dx